Now, our next speaker is a St. Joseph's Convent, St. Joseph's past student who has now taken up residence in Grenoble, France, where she works as a research scientist at the Xerox Research Center in Europe, the XRCE. Dr. Naila Murray obtained her Bachelor of Science cum laude in electrical engineering at Princeton University, and then went on to work as a doctoral candidate in the Color in Context group at the Computer Vision Center in the Universitat Autónoma de Barcelona. She was a visiting researcher at Xerox Research Center Europe, that's the XRCE, from 2011 to 2012, in the framework of a joint research project between Xerox and the CIC. Her research interests includes scene understanding, visual attention and image aesthetics analysis. Currently, her research focuses on fine-grained visual, categorization, and object detection. Dr. Murray has several patents, including a reweighing scheme for reducing visual burstiness. I believe burstiness, that's a new word? Technical word. Methods and systems for ranking images using semantic and aesthetic models, image selection based on a photographic style, convex clustering for chromatic content modeling, and system and method for image color transfer based on target concepts. So in short, it's how computers see, I believe. Right. And now, I'd like to invite Dr. Murray to give us a presentation, The Rise of the Machines, Big Data and the Learning Revolution.
Thank you very much for the introduction. So yes, as he mentioned, I work mostly in computer vision, which is getting computers to see and to understand the visual world in the way that humans do. But today I will talk a bit more broadly than this, because what I do is one aspect of a broader field of artificial intelligence, which is very closely related, especially these days, with machine learning. Can everyone see the slide? I'm not blocking anyone? Okay, so let me just give you a roadmap of what I'm going to talk about, very briefly. So this will be, my talk is going to be a very brief, very whirlwind tour of the what, the where, the why, and the how of machine learning. So this is, what is it? What is machine learning? Why is it interesting? Why is it useful? Where is it used today in our world? And very briefly and in a very nutshell point of view, how does it work? And then I will discuss some current challenges. So what do we talk about when we're saying machine learning? So to do that, we can break it down a bit. So what do I mean by a machine? It's something we're all familiar with, basically computers. So there are many types of computers that we all interact with on a daily basis. We have our PCs that we're all used to, our desktops or our laptops. We have servers, which are basically much more powerful ones. And then we have things that most of us have here today that we all use very interactively, our smartphones, which are much less powerful, but are certainly computers, and they're able to do many computations that would have seemed crazy just a few years ago. But we all can see the evolution of the phones we had 10 years ago to the ones we have today. So this is what I talk about when I mean machines, things that can make computations. And then when I talk about learning, we're talking about the ability to use past experiences, and these experiences can be in the form of some kind of data, to make predictions about new ones. So machine learning is simply allowing a computer to use past experiences, and these past experiences is in the form of data, in order to make predictions about new phenomena that might occur. So why is machine learning useful? Why is this approach useful? So let's take a step back to how we typically interact or make predictions about the world. So traditionally, we resort to basically the unreasonable effectiveness of mathematics. So this was a term coined by Eugene Wigner, who was a Nobel Prize-winning physicist. And his point basically was that mathematics, had this ability to describe the world in very precise, very accurate ways. So we can take some phenomena, we can observe it, we can extract data from it, and we can use a mathematical equation, a very short, concise equation, to describe this phenomena and to make predictions about the future. So to give one concrete example of what I'm talking about, we all are very familiar with, and it's very intuitive to us, the relationship between the speed at which we travel, the distance that we travel, and the time it takes us to do so. So all of us come here today this morning, said, okay, I need to come here, I'm traveling from home, it takes me this amount of distance, and I know I can't travel faster than the speed limit, and so therefore the time it takes me will be this much. So this is very intuitive, we all use it every day. And then we can make predictions. We can say tomorrow I know exactly, given traffic situations, I know exactly how long it will take me to get somewhere, given the speed I need to travel, and how much time I have. So this is very nice. So given that we can just take a very simple equation like this, and make predictions, can we do it in general? So let's say I want to make another type of prediction. Let's say I want to know whether next week Friday it's going to rain or it's going to be sunny. Can I take the same approach? Well, it turns out that it is extremely hard. It is extremely hard for human beings to say, predict weather patterns in the sort of nice formula that you have here. So the question is, how do we tackle these types of problems that are extremely complex and that at least today humans can't describe concisely? So this is where we go from the unreasonable effectiveness of mathematics to the unreasonable effectiveness of data. So this is a term coined by Peter Novick, who's currently a computer scientist at Google. And what this is describing is the fact that with enough data, even if we can't concisely explain or concisely summarize a phenomenon, we can certainly learn from past experiences and make predictions about the future. So this is what machine learning does. It allows us to use computers to discover relationships between variables. Because, for example, in the same way that previously we can understand very intuitively the relationship between speed, distance, and time, we know that weather is a function of temperature, is a function of pressure, and other variables. But for a human to understand the relationship between this is very complicated. And certainly there are other variables that we may not even be aware of. So this is what machine learning allows us to do. So let me give one example of something that I do, which is in the field of computer vision. So let's say we want a computer to be able to tell us every time President Barack Obama appears on the TV. How can we get a computer to tell us that, to alert us to, oh, he's on the television? So what the machine learning approach is to show the computer past images of President Obama. So you input into the machine an image, and you tell it this image contains President Obama. Then you show in another setting, in a different setting, and you show many such examples. So thousands and millions of examples in many different settings and many different scenarios. And you need to have a very varied data set, and this is what I would describe as a data set, because you need to be able to generalize to new unseen situations. And so at the end of the day, given this image, the computer should be able to say, I've seen this something very similar to this image before. I think this is an image of President Obama, and the machine alerts me. So where can we see examples of machine learning today? It is ubiquitous. It is everywhere. Let me just give you a very few examples, but there are many, many more. So one example is in pedestrian detection. This is another computer vision example, which is getting cars equipped with computers to be able to see pedestrians even before we do, and to react to them before we do. So these types of systems are in place today in several cars. For example, Volvo, Mercedes-Benz has these features. And so I'm going to show you one example of a car being able to detect a pedestrian and even prevent collisions.
Pedestrians and cyclists are the most vulnerable road users and are less likely to be identified by drivers. The Mobileye system identifies pedestrians and cyclists during daylight hours and can determine if the danger of a collision exists. In the event of a possible collision, the system issues an alert providing you with up to 2 seconds to brake and prevent an accident. Mobileye, our vision, your safety.
So this is actually a system that's in place, it's in production, people use it. And you see here is basically a camera that's set up, and this camera inputs images into the machine, into a computer, in real time, meaning as the user is driving. And the machine is able to see images of the scene and realize that I have seen this before, this is a pedestrian. And I've learned that this is a pedestrian, and I realize that the driver is not stopping in time, and I will stop the car for this. This is one example. Another one that I think maybe all of us, or very many of us have used, is in speech recognition and generation. Because those of us who have iPhones, maybe we have used Siri, or if you have an Android, you've used Google Now. And so you know that you can ask a question in natural language, you don't have to type, you can speak like you speak to anyone. And this smartphone can understand exactly what you said, can answer your questions, and even answer your questions in natural language. So here I can give a brief demonstration. If I can find my pointer. Here it is.
Who is the 21st President of the United States?
Chester A. Arthur was the
Okay, we go.
So there you see that this user was able to speak like it would speak to anyone, to speak to the smartphone and ask who is the 21st President of the United States. And very quickly, this machine can understand what the user said, actually look up the relevant information, and then return it to the user in the form of speech. Another example of image retrieval is a very interesting case that occurred a few years ago around an artificial intelligence called Watson. So Watson is a machine, it's an artificial intelligence that was designed by IBM. And this machine actually competed in Jeopardy. It competed with human competitors in Jeopardy. And let's see how it does.
Let's take alternate meanings for 200, Alex.
4-letter word for a vantage point or a belief. Brad?
What is a view?
Yes.
Alternate meanings 400.
4-letter word for the iron fitting on the hoof of a horse or a card dealing box in a casino. Watson?
What is Jew?
You are right. You guys pick.
Literary character, APB, for 800.
Answer. Well, there you go. And Watson, although you have $400, you know, of course, that you can risk up to the maximum value of you on board, and that is 1,000.
1,000, please.
All right, here's the daily double clue for you. Wanted for killing Sir Danvers Carew. Appearance pale and dwarfish. Seems to have a split personality.
Who is
I, yes, Dr.
So once again, you see that this machine was able to understand Alex Trebek, understand his question, look up the relevant answer, and then return it in natural language. And in fact, Watson went on to win that competition, and he won the $1 million prize. It's won the $1 million prize. And you can find many other examples where machine learning is evident. So I will give you a very, in a nutshell, view of how this works. And the answer really is simple, it's statistics. Basically, rather than trying to explain a phenomenon in a concise equation, you basically give a machine many examples of relationships between inputs and outputs, of inputs and outcomes. And this machine uses it to make statistics, and then it makes decisions based on probabilities. So let's say, for example, you want to train a machine to distinguish between President George Bush, W. Bush, and President Barack Obama. What do? You input many images of both of them, along with the identities of each. And then this machine will take in these images, will extract from the images relevant information, such as what is the color of the hair of this person, what is the color of the skin of this person, what is the shape of the eyebrows of this person, and many such characteristics. And it will make statistics over, it will compute statistics over these characteristics. And then when a new image comes in, it will say, given the characteristics I see in this image, what is the likelihood that this image contains either President Bush or President Obama? And this is really it. Of course, there are many complexities underneath it, but the basic principle is the same.
There's some overlap.
Between? Yes, of course. And generally, these problems are not so easy, so there tends to be a bit of overlap in between. So, what are the challenges in machine learning? What are the things that are barriers to progress? So, one is getting data. I've stressed a lot the fact that this runs on data, lots of data, terabytes and terabytes of data. As I explained before, if we want to get a computer to recognize a person, such as President Obama, we need to give it millions of images, maybe thousands, but certainly a lot of data. And so where do we get this from? A big answer is crowdsourcing. There are two components. One is mining data from the internet, and another one is crowdsourcing people to help construct the data. So where do you get this type of big data from? So let's say, for example, I want to once again make this recognition system. You can go to YouTube, you can type in President Obama, and you get thousands of videos with many, many images that you can use to input into a system. YouTube has millions of videos with many, many hours of video. So it's a treasure trove, really, of data of this type. Another example is in trying to have an information retrieval system, such as the Watson, which is the example I told you about the Jeopardy contestant. So actually, Watson, to get the answers he got when he was playing Jeopardy, he used many internet sources, one of which was Wikipedia. So if he was asked a question, he could very quickly go to the information stored in Wikipedia and understand and retrieve information that's contained there. Another example is in the domain of machine translation. I don't know how many of you have used Google Translate, but Google Translate works on machine learning. Basically, it takes examples that it finds, for example, on the internet, and uses it to make new translations. So one set of data for this is from the European Parliament, because the European Parliament is mandated to translate every video of a parliamentary session into all the member languages of the European Union states. So, and this is all public. So if someone wants to train a machine, they can simply go online and access, translations from tens of languages and use this to make predictions in the future. So really, the internet, the age of the internet has really facilitated the age of machine learning. And excuse me. So now that you have this data, it's not necessarily simple, it's not straightforward to actually use it. Because let's say, once again, let's go back to my example of face recognition. Even if you can go to YouTube and find videos of, for example, President Obama, the video is not going to be only him, not necessarily. You may have other people present in the video. So you can't simply put this into a machine and say, this is an image of Obama, because the machine might become confused, but I'm seeing two different people. So you need somebody to supervise the machine. And this is what's called supervised learning. So in the learning stage, the machine needs to have a bit of supervision to know, in this video at a certain point, this is Obama and this is not. And this is where crowdsourcing comes in. So crowdsourcing, there are many crowdsourcing platforms out there. The basic idea is that there are many, many workers, thousands and hundreds of thousands of workers all over the world who are signed on to these platforms and who perform tasks for a given price. So let's say, for example, I want to train this system. I can upload many images or many videos, and I can ask people around the world to annotate these images for me. So basically to say, for any image, can you tell me whether a specific person is in this image or not? And this is also a very key component to training these systems. Another example is reCAPTCHA. So probably all of you are familiar with trying to log into a system, and then you have some sort of anti-fraud system that tries to tell you to put in like a CAPTCHA, right? So they give you some sort of a puzzle to solve. So for example, you have to type in the letters that you see in an image, for example, right? This is CAPTCHA. So what reCAPTCHA does is it's very similar, but it tends to show you two images. It shows you one that it knows the answer to, and it shows you a second one that it doesn't know the answer to. So if you answer the first question right, it shows, okay, this is a human. Then it gives you a second answer, and this one, it doesn't know, but you're giving it the answer. So you are helping to perform translations of images. So this is another way that crowds are used to make these annotations. And in this way, you can capture millions of annotations in a very reasonable price. But storing data and learning quickly, it means that we're going to need a lot of very big and powerful machines. So, because we're talking about terabytes and terabytes of data that we need to store, and we need to access quickly, and we need to be able to use quickly. So what this means, so the types of systems that are used today that are really essential for machine learning involve computing clusters. So these are basically huge networks of connected computers, very powerful computers that are typically called servers. And so these are used to distribute processing and also to distribute storage, and to make the storage very robust. Another technique, another approach is making strong use of parallel computing. So typically when people are designing machine learning algorithms, they try to design the algorithm such that it's somehow modular. It can be split up into small pieces that can be sent separately into computers. And in this way, rather than having a set of things that need to be solved sequentially, one after the other, which takes more time, you can simply put them all in a parallel fashion, and you get orders of magnitude of speed up in time. Another fairly recent trend, let's say in the past 5 years or so, is the use of more specialized types of processing units. So these processing units are called graphical processing units, or GPUs, and they allow you to, rather than a traditional processing unit, which can make very complex calculations, but it takes some time, a GPU allows you to make many simple types of calculations. And it turns out, if you can design your machine learning algorithm appropriately, you can use these simple calculations rather than more complex ones. And then it allows you to use a certain type of processing unit, which is very efficient. So just to recap, machine learning has many successes in this day. It's used, as we've seen, in speech recognition. It's used to detect pedestrians in the cars that we drive. It's used in many factories for quality control. It's used in machine translation, such as Google Translate. It's used to predict stock market movements. It's used in medical imaging, for example, to detect pathologies in let's say, echografts and different types of medical images. And however, there remain some challenges, as I described. So, a lot of focus right now is in designing better machine learning algorithms. So what this means basically is algorithms that are more efficient, that are more accurate, and that can use less data to achieve the same outcome. And also we're very interested in designing better hardware. So these are advances such as I just described, the graphical processing units, and other types of very specialized processing units and chips that allow you to be much more efficient in terms of even energy, also space, and also efficiency in time. So that's it. Thanks for your attention, and if you have any questions, I'll be happy to answer.
Hi, Dr. Murray. I wanted to find out if, actually a couple of things. The statistical models that would be a basis of, let's say, discriminating Obama from others would be either discriminant analysis or logistic regression. The first question is, do you tell the machine which variables to pick? Like, for instance, do you say, take eye spacing take, let's say, length here, width.
So this is a very interesting question, because right now in many fields there's sort of a revolution going on in terms of what we would call feature representation. Because what you're describing, these things like the shape of the face, etc., these can all be considered features, right?
Yeah.
And typically the standard approach is to what we call hand tune them, so to design them by hand. So we say, we as a human, we know, as experts, let's say, we know that this is how we distinguish between faces. And so we give this input into a computer and tell the computer, this is the information I use, you use it, right? And then the computer has to decide which one it finds useful, which ones it doesn't. But now there's a trend in what is called deep learning, which I'm not sure if any of you have heard about. But deep learning basically is taking a more biologically inspired approach. So in the same way that as a baby is not told, or maybe it does not understand. It doesn't understand if you tell it at a certain age, when it's a few months old. This is a certain person, this is another person. Maybe not a few months, maybe a bit older. But the point is, many children can understand simply by repetition, simply by just seeing things, understand a lot. They learn to speak, they recognize people, etc. And the point is, rather than in the same way that we don't give children features, a bunch of features, and say recognize this person, the child just sees it. We want to get the machine to do the same thing. This is called machine learning, and basically what it is designing what are called artificial neural networks, which are basically algorithms that are a hope in some way to resemble the brain, in the sense that there are many neurons that are interconnected, and just with this very complex system that we certainly don't understand very well, but we can be inspired by it. You can simply show an image, you can simply show a computer an image without asking anything else. Just an image, and at the output you can get something like this.
That brings me to let me just clear this up to my second question. Do you ever give them not Obama?
You have to.
Well, you see, this is it. Because we did some work on identity verification, where we use neural networks, we use discriminant analysis, and compare them in terms of developing something that would differentiate between an authentic user and
a robot or something, yeah.
Well, no, not a robot, but let's say a fraud. So when you do that, you essentially base it on your measures, the error, and as you showed in the red and blue, is really of two types. When it fails to recognize a true user from a fraud, and so that somebody, let's say, will be locked out of their bank account because it doesn't recognize the person. And when it takes a fraud and treats them like a user.
A true user, yes.
Right. So false acceptance, false rejection rates are the two error calculations. And we did compare this neural networks with discriminant analysis, and for that, because the data that was being fed or is being fed to the computer comes from biometrics and haptics. So there's a screen, you can write on it, and we had like 126 variables, and you trim it down. And in comparing the methods, you essentially look at the misclassification. So the discriminant analysis model for us in that worked a lot better. But as you said, it involves really ensuring that you put in then the anti-Obama or the anti-Bush. Now, if you have multiple people for whom you want to differentiate it, like you might differentiate Obama from a white person, but you also have to differentiate him from a black one. So then you couldn't use logistics, you'd have to go to discriminant. But in something like that, some of the more orthodox statistical models might work a little bit better than
So this is quite true. So the thing about deep learning, which is what I just described, this sort of new approach to learning, is that it requires a lot of data, just in the same way. It requires even more, because it needs to think a bit more. in some situations, if you tell it that the size, like the shape of the face is important, then it has a bit of a head start.
Yeah.
But if you start from the beginning, then it needs much more data. But if you reach that critical point, you can get extreme improvements over hand-doing things.
Yes, thank you, Dr. Murray. I believe we have a question in the back there.
Yes, it sounds like this process has a lot of human input into it. It's like humans working together with machines to a certain extent.
Yes, yeah.
So in essence, the human mind is not becoming obsolete.
Not at all. Not yet. Not yet. If we start to get computers to be able to think about thinking, then we will see. But at this point, there's what I call supervision.
Yeah, Mr. Watus.
We had another one, yeah.
Yes,
Yeah.
Dr. Murray, congratulations, you're young and very valuable. I wrote a science fiction some time ago, the only one. And the more I hear topics like what you're talking about, is the more I'm convinced that what I wrote about, some aspect, is relevant.
You said you wrote a book about science fiction?
Yes,
Ah, interesting.
and from my imagination. I hope it is studied what you imagine. However, one of the things I've talked about, you take the lie detector, right? I think that's something I believe operates on one's emotion. You know what the lie is about, I might be wrong. But I'm saying that if the same machine you're talking about, and we talk about crime, and all this terrorism, and if you had a machine which is so programmed that let's say coming to customs, and you ask the question, initially you put your thumb print, right? And you take maybe a perspiration. But when you ask the question, that machine will pick up the difference in your temperature, your pulse. Is this possible?
It's certainly possible. I believe it might even be in use right now.
Big pardon?
I believe it might even be in use right now.
Well, I hope you
Using, sorry?
I hope you develop.
Lie detectors do exactly.
No, I'm talking about
But,
I'm talking about two variables.
yes, for example, the same way that we use variables to recognize people, we can use variables to recognize, for example, lying, right? So you can show a machine examples of people who are lying and people who are telling the truth. You can give it, the machine can learn, when somebody's lying, technically, statistically, it's likely that they will have certain characteristics. They might be higher temperature, they might blink more, etc.
We have time for one more question. Anybody? Christian in the back.
No, I was just curious, it's not quite what you're talking about, but what did you think of Stephen Hawking's concern and about the rise of artificial intelligence and the end of humanity as we know it?
So I think, well, I guess I beg this question with my title, but I think, like most technologies, it can be used for good or for bad. The internet, for example, is something that I think most of us now can't even imagine living without, whereas, 20 years ago, none of us, very few of us used it. But of course, there are very negative sides to that, in terms of distribution of a lot of illicit material, etc. It makes many things easier, it makes many things harder. And so I think we just have to be vigilant. And we can't be afraid of moving into the future when we see the types of things we can do. When we think of how we can, the amount of people that die every year in car accidents, we can really do a lot to improve the world. But we have to be vigilant because like any technology, it's extremely powerful. And in the wrong hands, things can go quite badly.
All right, thank you, Dr. Murray, for that presentation. I believe this is your first presentation in Trinidad and Tobago.
Yes.
Yes, it is. We'll give her another round of applause for that.